This figure shows the complex exponential signal sequence x of n is e raised to j omega n, which can also be represented as x of n equals to cos omega n plus j sin omega n. Here n is the sample index and omega equals to pi by 4 is the angular frequency. At sample n equals to 0, x of 0 is e raised to j omega 0, which can also be evaluated as cos of 0 plus j sin of 0 or 1 plus j0. At n equals to 1, x of 1 would be e raised to j omega 1 or cos of pi by 4 plus j sin of pi by 4, which can be evaluated to 1 by root 2 plus j by root 2. The new position of x1 with respect to x0 is that we rotate anti-clockwise by pi by 4 from x0. For n equals to 2, x of 2 would be x of 1 into e raised to j pi by 4. That is, we rotate anti-clockwise by pi by 4 from x1. We can keep on proceeding for n equals to 3, 4, 5 and so on, and we conclude that as n increases we rotate the phasor from its last position n-1 by pi by 4. We now are again reminded that omega has a unit of radians per sample, and as in our example omega is pi by 4, a positive value, which means that we are rotating counterclockwise for pi by 4 in each sample. At n equals to 8, the phasor lands on the position of x equals to 0. This also demonstrates that for this case, we have a periodic signal x of n plus 8 equals to x of n for all values of n, and that the signal is periodic with a sample period of 8. In this figure, however, we will animate the rotating complex exponential with omega equals to minus pi by 4. And in this case, we see that the sample index, when increased from n-1 to n, the phasor rotates in a clockwise fashion with angle of pi by 4.